This is my trigonometry course. Today we're going to continue to explore the 6 basic trigonometric functions. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. In the previous class, we determined the value of trigonometric functions with positive angle measures, but we didn't go into negative angle measures, as you see here. Remember, when you evaluate a trigonometric expression geometrically, you draw a triangle on the xy coordinate system, and you always start on the positive part of the x-axis and rotate counterclockwise. But now we have a negative angle measure, so now we rotate clockwise. So positive angle measure is counterclockwise, negative angle measure is clockwise. And all of the principles that we learned in the previous class apply. We're just rotating in the other direction. So this is not something we need to spend a lot of time on because it's pretty easy. But let's just do some practice problems. So we're going to start on the positive part of the x-axis, and we're going to rotate clockwise because it's a negative angle measure. And again, we don't have to use a protractor here. It doesn't have to be that exact. That's approximately 60 degrees. So we write negative 60 degrees. And that just happens to be a special angle, which creates a special triangle. If that angle is 60 degrees, then this angle is 30 degrees. And of course, you see we have a 30, 60, 90 degree triangle. And that means that whatever this side is, we'll call it x. The side opposite 60 degrees has to be that number times root 3. And of course, because the triangle is going down, it's going to be negative x root 3. And the hypotenuse is double that number. Now, it doesn't matter how big or small the triangle is. That's very important to understand. It doesn't matter how big or small the triangle is. It just matters what the relation between the sides is. Because sine, all these sine, cosine, cotangent, all these trigonometric functions are ratios of the sides. So once you determine what the angles are, and the angles are all determined by this number here, because these functions are defined only for right triangles, so we know that angle's a 90-degree angle. Once you determine what this angle is, that determines all of the angles based on the triangle sum theorem, and therefore it determines the shape of the triangle, and thus the ratio of the sides. I know that's a lot to take in, but that's just the way this works. So now, sine of a negative 60 degree angle is equal to the opposite side of the red reference angle divided by the hypotenuse. And remember, the hypotenuse is always positive. It's always defined to be positive. That's very, very important. I should have emphasized that more in the previous class. The hypotenuse is always positive. So the x's cancel out, and the ratio is negative root 3 over 2. Let's try another one of these problems. Now we have a negative 225 degree angle. Now normally we rotate counterclockwise, but now we rotate clockwise because it's a negative angle. So that's 90 degrees, 180, and we're going to go a little more to get to that 225 degree angle. And we have to calculate this green angle in here. That's the reference angle. In the first quadrant, or in this case, when you have negative angle measures in the fourth quadrant, the reference angle is equal to the actual angle. But in other situations, you have to calculate the reference angle. So the red angle is negative 225 degrees. And you know that from this horizontal to this to the same horizontal, you have a 180 degree rotation angle measure. So if you take the red angle and subtract the blue, for now just assuming they're both a positive, then you get 45 degrees. So our reference angle, the most important angle, is 45 degrees. But if that angle is 45 degrees, then of course by the triangle sum theorem, this angle must be 45, and of course we have a special triangle. The sides opposite the 45 degree angles, we're just going to call those x, and of course this side is called negative x because it's going to the right. It's on the left side of the y-axis. This side is positive because it's on top of the x-axis. And whatever those sides are, the hypotenuse is that number times root 2. Again, this is just the basic 45, 45, 90 degree triangle theorem, and over here the 30, 60, 90 degree triangle theorem. These are all things that we covered in the previous classes. These are the basic theorems that we need for this course. So cotangent, if you recall, and if you don't have these, go ahead and take a picture. Cotangent is defined to be the side adjacent to the reference angle divided by the side opposite the reference angle. So the side adjacent to the green angle is negative x, and the side opposite is x. The x's cancel out, and we see our answer is negative 1. So we're doing the same exact problems that we did in the previous class. The only difference is our angle measures are negative, so we're rotating clockwise rather than counterclockwise. So remember, the reference angle is the most important angle because that tells us what type of triangle that we have. They're all going to be right triangles, but are they going to be 45, 45, 90s or 30, 60, 90s? You have to calculate that reference triangle, and the values of the trigonometric functions are based on I should say they're centered around that reference angle. So the reference angle is always the angle between the x-axis and the terminal side of the angle in standard position. Okay, let's try another one of these problems. So we're going to rotate negative 150, which takes you to about there. Again, you don't have to get a protractor out. So what is the reference angle? Again, the reference angle is the angle between the x-axis and the terminal side of the angle in question. So that is going to be 30 degrees. How do I know that? Well, because we know that a half rotation is 180 degrees. So you just subtract 150 from 180 and you get 30. That's what you need there to fill that gap. This angle's got to be 60, and if this side is x, then this side is x root 3, and this side must be double x. But both of these sides have to be negative. Why is that? Because the adjacent side is to the left of the y-axis, and the opposite side of the reference angle is below the x-axis. Again, the hypotenuse is always defined to be positive. Very important to remember that. So cosine of a negative 150 degree angle is equal to, and again, I'm going to give you one more chance to get a screenshot of these. You should know these by now, but I'm just giving you every opportunity to see those. Cosine is defined as the adjacent side to the green angle divided by the hypotenuse. So our answer is negative root 3 over 2 because we don't really care how big the triangle is. Those x's cancel out. We just want the relation between the sides so we can find the ratio of the sides. So let's do one more of these problems. And then you can try some of these on your own. Again, this is not something we have to spend a lot of time on because you can see it's pretty easy. It's the same thing we were doing in the previous classes. So we're going to rotate clockwise 315 degrees and draw a reference triangle. And if this red angle is negative 315 degrees, then what is the leftover green part? Well, you just take a complete rotation because the red angle plus the green angle make up a complete rotation. A complete rotation is 360 degrees. Just subtract 315 from 360 and you get 45 degrees. So of course we have another 45, 45, 90 degree triangle. I'm creating these, or I'm writing these problems so that we do not have to use a calculator. Because if we have to use a calculator, then we don't really demonstrate any of the points that we're trying to learn. So both of those legs of the right triangle are positive because it's in the first quadrant. The adjacent side is to the right of the y-axis. The opposite side is above the x-axis. And cosecant is defined as the hypotenuse divided by the opposite side. So the answer is root 2. So there you go. So as you can see, this is pretty easy. It's just the same thing we were doing before, except because we have a negative angle measure, we're rotating clockwise instead of counterclockwise. So now it's time for you to try. This is going to be not only educational because it's going to show you how to calculate the trigonometric values of negative angles, but it's also going to help you to review what we did in the previous class. So go ahead and try number 5, and I'll leave those 6 trigonometric functions in the window, and when you come back, we'll do it together. Okay, we're back. So we're going to rotate negative 135 degrees, which would bring you to about there. Again, it doesn't have to be perfect. And we have to calculate the reference angle. Well, to fill in the gap here between the x-axis and the terminal side of the angle in question, we need a 45-degree angle. Again, that's just basic arithmetic. So that means by the triangle sum theorem, this angle is 45, and of course this side is x, but it's negative x because the triangle is going to the left, and it's negative x on the other side because the triangle is going down. And of course this side must be x root 2. Again, it's a 45, 45, 90 degree triangle. So tangent of a negative 135 degree angle is equal to the side opposite the green reference angle divided by the side adjacent to the green reference angle. So the x's cancel out, the negatives cancel out, and you're left with 1. So if you got that right, perfect. Excellent. If you didn't get it right, that's okay. You can try the next one. Go ahead and attempt number 6, and when you come back, we'll do it together. Okay, we're back. Negative 330 degrees means that we're going to rotate clockwise about to there. Again, it doesn't have to be a perfect rotation. It doesn't have to be exactly 330, just estimate. And then, of course, the most important thing for us to calculate is the reference angle. What is this green reference angle? Whoops. That's going to tell us everything. That's the angle between the x-axis and the terminal side of the angle in question. So you just take 330 or 360, a complete rotation, and subtract 330, and we get obviously 30 degrees, which means this angle is 60. And our 30, 60, 90 degree triangle theorem tells us if this side is x, then the side opposite 60 is x root 3. And the hypotenuse is 2x. And these sides are all positive because we're in the first quadrant. And secant is defined to be the hypotenuse divided by the adjacent side to the green reference angle. But we do have a problem. We can cancel out the x's, but we have a root in the denominator. So we have to multiply both sides of the fraction by root 3, and that rationalizes the denominator. Now, if you have trouble rationalizing the denominator, then you can go to the previous classes. We reviewed this in previous classes in this course. but you need to get to the point where you can do that quickly. Rationalize the denominator quickly. I know that it's a pain having to do that, but you need to get used to it pretty quickly here. Okay, so if you got that one right, try number 7, and when you come back, we'll do it together. All right, we're back. So now we're going to rotate negative 145 degrees. That puts us in the 4th quadrant. And this is the only case where the reference angle is equal to the actual angle. At least in the case when you have a negative angle measure. If you have a positive angle measure, then in the 1st quadrant, the reference angle is equal to the actual angle. Whereas with negative angles, the 4th quadrant is the case where that occurs. So this angle must be 45 degrees. And of course we have a 45, 45, 90 triangle. This side is positive x, but this side is negative x because that side is going down. Just like, you know, calculating or finding coordinates. You know that if you have a point here, the x coordinate is positive, but the y coordinate is negative. So sine is defined to be the opposite side of the red reference angle divided by the hypotenuse. And we can cancel out the x's, so we have a negative 1 over root 2. Problem is, we need to rationalize the denominator, so we multiply both sides by root 2, and we have the following expression. So if you got that right, perfect. Again, this is mostly just review of what we did in the previous class. Go ahead and try number 8, and when you come back, we'll do it together. Okay, we're back. Okay, let's rotate negative 240 degrees. That would bring us to about there. So remember, the reference angle is always the angle between the x-axis and the terminal side, this green angle here, but we have to calculate what the measure of that angle is. So the way that we do this is we calculate the measure of this half angle, or half rotation, which is 180 degrees. And we know that if we subtract the blue angle from the red angle, we get 60 degrees. There's a lot of different ways to think about that, but it's really just basic arithmetic. So that angle is 60 degrees, which means, of course, that this angle up here is 30. And this side, if it's x, then this side is x root 3. That's the 30, 60, 90 degree triangle theorem. And this side has to be negative because it's to the left of the y-axis. Okay, so now we're ready to calculate. Cosecant is the opposite side, or excuse me, the hypotenuse divided by the opposite side of the green reference angle. The x's cancel out. But the problem is we have a root in the denominator. Multiply both sides of the fraction by root 3, and there you go. So that was just some review of the previous class. What we are doing here and in the previous class is the most important thing in this course. So it's good to review, but it's also good to get an idea of how negative angle measures work. You can see it's pretty easy. It's just the same principles. The reference angle is calculated by determining the angle between the x-axis and the terminal side of the angle in question. So you probably noticed that what we learned in the previous class, along with what we just did, is a very strange thing to do, to flip these triangles around in the 1st quadrant and 2nd quadrant and 3rd quadrant, and some side lengths are negative, and you have to find the reference angle, and it just doesn't make a lot of sense. And that's why this is the most difficult part of the course. it's not that, as I mentioned in the previous class, it's not that it's difficult to do the problems. You can see that this is not that difficult once you learn how to do it. But understanding why we're defining these functions in this way is really not something that's obvious. It's not obvious to figure out why we're doing this. But again, it's going to become more apparent as we go into upper math and engineering and science courses. Well, now things are going to get even more strange. Now we're going to deal with something called that I call collapsed triangles. We're going to deal with angle measures that are multiples of 90, or in some cases 0. These are called quadrantal angles. That's one way to name them, but that name is not really used very often in the math curriculum, so it's just a fancy name you don't have to remember. But let me demonstrate what is happening here. Let's say you try to calculate the sine of a 90-degree angle. Well, let's start off with 40 degrees. Of course, these functions are defined for right triangles and right triangles only. And sine 90 is the side length of the opposite side, the length of the opposite side of 40 degrees, divided by the hypotenuse. And notice that the yellow side is always going to be smaller than the hypotenuse. So the ratio of the yellow and the green is always going to be less than 1. The hypotenuse is always going to be bigger. But what if we allow this angle to approach 90 degrees? What's going to happen? Well, let's make an angle that's really close to 90 degrees. That angle is, what does that angle look like? Maybe 70 degrees. We're getting closer, a lot closer. And notice what's happening to this side. This side got a lot smaller. And the yellow side and the green side are starting to be almost equal to each other, the hypotenuse and the opposite side. Let's make an angle measure that's even bigger so that the hypotenuse is going almost straight up. It's hard to even draw a triangle in this case. You can see that I'm not even doing it very well. But now our angle is, I can't even fit it in the triangle. Let's say that the angle is, I don't know, 80 degrees. Look what's happening. This side, again, it's almost disappearing. And this side, this opposite side, and the green hypotenuse, they're getting to the point where they're almost equal. When this angle actually reaches 90, what happens to the triangle? Well, the triangle actually collapses. There is no triangle. So it really doesn't make any sense to define this function when you plug in 90 degrees. It doesn't make any sense to really define this expression for a 90-degree angle, because there is no triangle. These functions are defined for right triangles, but when you collapse the triangle, there is no triangle. But for reasons that you're going to learn when you go into science and upper math courses and engineering courses, if you do choose to be an engineer, you're going to find that mathematicians and scientists and engineers have decided to define this value as 1, because as this angle approaches 90, as we mentioned, the yellow side, the opposite side, and the green side, the hypotenuse, they get to the point where they have lengths that are almost equal. So this function, as it approaches 90 degrees, the ratio of the opposite side and the hypotenuse approaches 1. It gets closer and closer to 1, because if you divide this side by this side, whatever you want to call it. We can call, usually this side is called y, this side is called r. If you divide y and r, and they're almost equal lengths, then the ratio is going to be very close to 1. So as the angle gets closer and closer to 90 degrees, the ratio of this side and this side comes closer and closer to 1. So for convenience, mathematicians have decided to just simply define the sine of a 90-degree angle as 1. And that is very confusing. It's not exactly obvious why they would do that. But again, for now, all you have to know is it's just convenient to define the function that way. I call these collapsed triangles when you try to calculate the trigonometric value of an angle that is a multiple of 90. So here's an example. If you put this triangle in the first quadrant and you have a 45-degree angle, then you increase to 70, then you increase to 87, what's happening to the triangle? It's collapsing. Here's another example. When you approach 180 degrees, you have 112, 148, and then 171. What's happening to the triangle? It's collapsing. So sine is defined as the opposite side of the reference angle, and in this case the reference angle is this green angle here. So the opposite side is this yellow side, and the hypotenuse is the green side. But look what happens as the angle approaches 180 degrees, the yellow side is approaching 0, or the yellow side length is approaching 0. And so sine is the yellow side, the opposite side, divided by the hypotenuse. So if the yellow opposite side approaches 0, mathematicians just assume that it is 0 when the angle actually gets to 180 degrees. And so the sine function approaches 0. So we just define sine 180 degrees as 0. And by the way, I forgot to write up here, sine 90 is equal to 1, and sine 180 is equal to 0. So I know that this is very, very strange. In order to understand or to figure out what these values are when the triangles collapse, you have to picture a triangle collapsing as you approach 0 degrees or 90 degrees or 180 or 270 in this case, or 360. The triangles collapse, but it's very difficult to picture that triangle collapsing in your head. A lot of students have difficulty understanding, what is going on. And for that reason, it's really not the best method to picture a collapsing triangle. You might be able to do that. Sine 270 is equal to -1. Again, it may not be obvious why that is. Sine is defined as the side opposite divided by the hypotenuse, as we mentioned many times already. So it's the yellow side divided by the green side. But notice as we approach 270, just like when we approach 90 degrees, the yellow and green side are getting closer and closer together when it comes to their length. But because the triangle is pointing downwards, the opposite side is negative. And so we define sine of a 270-degree angle as -1. Because as the angle approaches 270, the sine value doesn't approach +1, it approaches -1. So we have the same logic down here. The triangle collapses, but the opposite side of the reference angle is going to be 0, so we define sine 360 degrees as 0. But again, this is all very, very difficult. It's not easy to understand or to picture these triangles collapsing. The good news is we have a better way to think about it. What we do is we actually graph the sine curve, we allow the horizontal axis to be angles and the vertical axis to be the ratio of the side opposite and the hypotenuse. So notice that the sine curve goes up and down between -1 and +1, -1, +1, -1, +1. That's because the hypotenuse is never going to be bigger than the side opposite in a right triangle. The hypotenuse is always the biggest side. So if sine is defined as the opposite side divided by the hypotenuse, the ratio can never be bigger than 1 or smaller than -1. Now, this curve actually explains to us a little bit about why these values are defined the way they are. You see these green dots? These green dots are where the triangles collapse. And we see that if we graph this curve, it approaches 1. So for convenience, engineers and scientists and mathematicians have just defined the sine of a 90-degree angle. If we go out 90 degrees, go to the right 90 degrees, then we define the y value to just be 1. So that point is 90 degrees. If you were to write the coordinate, it's 90 degrees, comma 1. That's that point there. So this curve is very useful, but we don't want to have holes in the curve where the triangles collapse. So we just define these values to be real numbers. Now again, I know what you're thinking. You're thinking, this just seems bizarre. Why are we doing this? Well, again, it's not exactly obvious why we're doing this. This first part here is where you find a real triangle, a real right triangle. But when you go beyond that, when you go beyond over here, you're talking about triangles that can't possibly exist unless you come up with those clever ways to define them using negative side lengths and moving the triangles into different quadrants, quadrant 2, 3, and 4. So when we put when we define the functions this way, we can graph this curve, and this curve appears in nature all over the place, and in engineering and science. So this curve really helps us to find the values of trigonometric functions with angle measures that are multiples of 90, because these green dots show us what the values are. So rather than dealing with collapsed triangles, which is very difficult to picture in your head, it's better to just memorize these curves. So let's do some practice problems. And that explanation may have seemed very convoluted and difficult to understand, but doing these problems is not difficult. So regardless of whether or not you understood what we were talking about, you still need to be able to do these problems. So let's try number 9. The sine of a 270-degree angle, that's a multiple of 90. 3 times 90 is 270. So what we do is we go to our curve, and we count out 270 on the x-axis, and then we ask the question, what is the y value on the curve? So if x is 270, what is the y value of the corresponding point? And that is -1. You go down 1 unit. So sine of positive 270 is -1. Sine of a 360-degree angle, well, you just go out 360 degrees, and then you ask yourself, what is the y value of that point? And well, it's 0, because it's on the x-axis. Sine of a 0-degree angle, well, you just go out 0 degrees, which means you don't go anywhere. You stay on the y-axis, and you ask, what is the y value of that point on the curve? And the y value is 0. So as you can see, this is pretty easy. Now, if we have a negative angle measure, that means we go to the left. We don't go to the right over here. We go to the left over here. So let's go out 90 degrees, and 90 degrees is one box, although I didn't label it. What is the y value of the point on the actual curve? Well, that's -1. We had to go down 1. So sine of a negative 90-degree angle is -1. So if you'd like, you can try number 13. You're going to go to the left because it's a negative angle. And remember, each box is 90 degrees. So you're going to go there. What is the y value of the point on the curve? If you said it's 0, you're correct. Because that point on the curve is on the x-axis. The y value is 0. Try number 14, and when you come back, we'll do it together. Okay, we're back. We're going to go out 90, 180, 270, 360, and 450. Again, add 90 to 360, and you get 450. What is the y value of the corresponding point on the curve? 1. So sine of 450 degrees is 1. So if you got that right, perfect. So we have not learned the cosine curve yet. Notice that it looks very similar to the sine curve, except it's moved 90 degrees to the left. And again, the horizontal axis is the angle measure in the function, and the vertical axis is the ratio of the adjacent side of the reference angle and the hypotenuse. And so that ratio is never less than -1 or greater than +1. The ratio just goes up and down, up and down. So now we're going to go to the cosine curve, and I'm going to allow you to do all these problems. So I want you to do problems 15 through 20. Use this curve. It's a different curve, but it's very similar. And when you come back, we'll do it together. Okay, we're back. So if 90 is the x value, what is the y value? So you go out 90 degrees and you see the y value of the point on the curve is 0. So cosine 90 is 0. Cosine 180, go out 180 and ask what is the y value of the point on the curve, the corresponding point. Well, that is -1. So if you got that right, excellent. Cosine 270, well, we just go out 270, which is 3 boxes, and ask what is the y value of the point on the curve. Well, it's 0, because the curve goes through the x-axis at that point. Cosine 360 degrees, you go to the right 360 degrees, and what is the y value of the corresponding point? 1. Cosine 0 degrees, you don't go anywhere, we just stay here. What is the y value of the point? Well, you have to go up to here. The y value is 1. So this is just how we calculate the values of these trigonometric functions when the angles are multiples of 90. All right, so if we have a negative 90 degree angle, we go to the left 90 degrees, and what is the y value of the point on the curve? 0. So if you got those answers, perfect. If you made a mistake, you could just go back and see what you did wrong. Okay, so let's try a few more graphs here. Now we're going to move to the secant graph and the cosecant and tangent graphs. If you want to calculate the secant of an angle that is a multiple of 90 or possibly 0, then again you just use the secant curve. Now we have not learned the secant curve, nor did we learn the cosine curve, so these are new curves that we're learning. And as you learn more about these curves, you're going to be able to memorize what they look like, but don't really worry about that now. I'm going to give you the graphs. So this is what the secant graph looks like, and notice you see these yellow dotted lines. What are these? Do you remember what these are called from my intermediate algebra course? These are called asymptotes. The red graph approaches those lines, but it never touches them. And an invisible line that the graph approaches but never touches is an asymptote. That's a line. Now sometimes graphs do cross asymptotes, but that's only if you're not dealing with a function, or you're dealing with a horizontal or a diagonal asymptote. So let's calculate secant 180 degrees. So we're going to go 180 degrees to the right, and the corresponding point on the the y value of the corresponding point is -1. So secant 180 degrees is -1. I know this curve is very strange. You haven't seen this yet, but this is just how you calculate the value of trigonometric functions with angle measures that are multiples of 90. So secant 90, we're going to go out to the right, but notice we have an asymptote there. So the graph is not defined on that asymptote, so we just say undefined. Number 23, we're going to go 270 degrees to the right, and again we have an asymptote. The red curve is not even defined on that asymptote, so we say, again, undefined. Secant -90, again we have another asymptote, so the function is not defined. Secant 0 degrees, well, if we don't move out at all, then the corresponding point is here. And the y value of that point is +1, so secant 0 degrees is actually +1. Secant -180, well, we go out -90, -180, and the corresponding point on the curve has a y value that is equal to -1. So there you go, it's the same principle. Now, I know what you're thinking. You're thinking, well, how am I going to remember this graph? Well, you don't have to. I'm going to give it to you, and later on in the course, we're going to study this graph in more detail, and you'll be required to remember it. But for now, you can just use it to calculate the values of trigonometric functions when the angle measure is a multiple of 90 or 0. So go ahead and try number 27, and go ahead and do 27 through 32. When you come back, we'll do them together. Okay, we're back. So let's move out 90 degrees to the right and ask, what is the y value of the corresponding point? Well, the y value is 1. If you got that right, good. Move out 180 degrees. What is the corresponding y value of the point on the curve? Well, there is no point on the curve. That's an asymptote. So the function is undefined for a 180 degree angle. Move 270 out, and what is the corresponding y value for that x value? The y value is -1. And if the angle is 0, what is the corresponding y value? Well, there is no y value. There's an asymptote when x is equal to 0. So we say the function is undefined for that angle measure. -90, we go to the left one box, and what is the corresponding y value of the point on the curve? It's -1, because we had to go down to get to the curve. Cosecant 360, move out 90, 180, 260, 360. We have an asymptote there, so again, it's undefined. All right, so if you got those answers, good. So now we're going to move to the tangent curve. Again, this is a curve we've never seen. It has some asymptotes, and you can see that the range is actually any real value, because the graph goes up and down forever. The range is kind of limited here because the y values cannot be between 1 and -1. But this is the same principle. We use this curve to calculate the values of functions with these multiples of 90 angle measures. So tangent 180, we move out 180, and what is the value? It's 0. The y value is 0. Tangent 90, we're going to move out one box, and there's an asymptote there. So that means that the function is not even defined. So we just say undefined. Tangent 0 degrees, well, if we don't move at all, then we have a point on the x-axis, so the y value is 0. Tangent negative 270, we'll move out to that asymptote, and we can see that if there's an asymptote, the function is not defined. Tangent negative 180, we're going to move out here, and the corresponding y value of the point on the graph is 0. Tangent 360, we're going to move out, and the corresponding point on the curve is 0. So there you go. So the cotangent curve looks almost exactly the same as the tangent curve, except the curve is orientated in if you're going up from right to left rather than left to right. And instead of going through the origin, there's an asymptote on the origin. Again, we're going to study these curves in more detail later on. Go ahead and try number 39 through 42, or actually 43. When you come back, we'll do it together. Okay, so 90 degrees, we're going to move out to the right 90 degrees, and that point on the curve has a y value of 0. So this is just how we calculate these multiples of 90-degree angles. Cotangent 180, we're going to go out 180, and there's an asymptote, which means the function is not defined for a 180-degree angle. Negative 90, we go out one box, and we see that the y value of the corresponding point is 0. Cotangent 0 degrees, well, if we don't move out, we are just left on an asymptote, and the function is not defined. So we say undefined. And cotangent 270 degrees, we're going to move out to here, and we see that the point on the curve has a y value of 0. So if you got those right, excellent. So we covered negative angle measures and collapsed triangles. When you do the homework, I'm going to give you those curves so you can calculate the values of the collapsed triangles. If you want, you can also think of these you can calculate the values by thinking of collapsed triangles. That's one way to do it. But generally, students are going to want to memorize these curves rather than thinking about collapsed triangles. So now we're going to cover something called coterminal angles. A coterminal angle is two or more angles in standard position whose terminal sides have the same location. So what that means is if you have, say, a 50-degree angle in standard position, you'll find that a 410-degree angle, also in standard position, has the same terminal side, meaning the terminal side is in the very same location, going off to the right, up and to the right. Also, a negative 310-degree angle has the same terminal side, or I should say the side is in the same location. Because the terminal side is in the same location for every one of these angles, they're called coterminal. They all have the same terminal location for that purple side. Here's another example. 90, 450, and negative 270, they all stop going directly upwards, the terminal side of the angle. So how do you calculate coterminal angles? If I want to find a bunch of coterminal angles, how do I do this? Well, it's very simple. You take your first angle there, and you simply add 360 to it. You start there and you go all the way around 360 degrees. Well, in this case, it would be positive 360. If we're going to add 360, you go all the way around till you get to the same point, and there you have your 410-degree angle. 360 plus 50 is 410. That's how I found that coterminal angle. Now, if I go in the opposite direction, if I go 360 degrees clockwise, then I get the negative 310 degree angle. Because if you subtract 360 from 50, then you get negative 310 degrees. So that's going the other way. So all you have to do is just add 360 and then add it again and then add it again, or you can subtract it and then subtract it again. You'll just keep getting coterminal angles. And one thing that's very important to understand is that there's no end to what these angles can be. You can have an angle that is 1 billion degrees. You can just keep going around and around and around over and over again. There's no limit to the angle measures that you can create in standard position, because you can just keep going around and around and around. Here's another example. We have our terminal side of the angle going to the left. In each one of these cases, if you rotate 180 degrees, and remember, you always have to start on the positive part of the x-axis. If you rotate 180 degrees, the terminal side is right on the x-axis going to the left. But if you rotate negative 180, meaning clockwise, again, your terminal side is going to the left on the x-axis, so it's a coterminal angle. These are both coterminal angles. But if you rotate 180 degrees and then rotate 360 more degrees, 360 plus 180 is 540. But again, your terminal side is still at the same position on the x-axis going to the left. So those are coterminal angles. So now let's just do a little practice with this. You're going to find that this is very easy. Most of what you do in the trigonometry curriculum is pretty easy. It's not going to be that difficult. It looks very difficult, but it's really not. So it says here, the measures of angles in standard position are written below. Find the measures of 3 coterminal angles in standard position. So if we have an 80-degree angle, let's find our first coterminal angle. We're just going to add 360, and we get 440 degrees. That's the measure of a coterminal angle, assuming that the angle is in standard position. Now we can subtract 360. Why not subtract 360? Again, if you do a complete rotation in either direction, clockwise or counterclockwise, you're going to have the same stopping point. So 80 minus 360 is negative 280 degrees. So now we can take negative 280 and we can either subtract 360 to get another coterminal angle, or we can take this angle and add another 360. I'm going to add another 360 to 440. Again, there's multiple ways to do it. And then I get another coterminal angle. Whoops. So 360 and then add another 360, and we get 800 degrees. So this is very, very easy. All we're doing is just adding 360 or subtracting 360 to get coterminal angle measures. So let's try the next problem. We have 0 degrees. So a coterminal angle measure would be 0 plus 360. Another coterminal angle would be 0 minus 360, so negative 360 degrees. And if you graph these out in standard position, you can see that the terminal side is going to be at the same exact position. So we can also add 360 and then add it again to get another coterminal angle. Then we have 720 degrees. So again, this is just basic arithmetic. The most important thing is to understand the concept that we're just rotating around until we get to the same terminal side. Okay, so now we have a negative 235 degree angle. Let's add 360 to that. If we add 360 to negative 235, we get 125. So negative 235 plus 360 is equal to positive 125 degrees. And if we add 360 again to 125, we get 485. And if we take this number, actually let's take negative 235 and subtract 360. You don't really have to write the degree symbols because that would get kind of tedious. So negative 235 minus 360 is equal to negative 595 degrees. So this is just basic arithmetic. Go ahead and try number 47, find 3 coterminal angles. And when you come back, we'll do it together. Okay, we're back. So one coterminal angle measure is 200 plus 360, which is 560 degrees. We're finding the measures of coterminal angles. We can subtract 360. You might get different answers. There's actually an infinite number of answers. But these are some of the answers you would get. And another coterminal angle is an angle if we subtract 360 twice. You could add it twice, but you can also subtract it twice. 200 minus 360 and then minus 360 again is negative 520. So those are some possible answers that you could have gotten. Okay, try number 48, and when you come back, we'll do it together. All right, we're back. So let's try adding 360. And of course we get positive 45 degrees. Let's try adding 360 again. So we add it once, and then we add it twice, and we get, that would be 405 degrees. And let's try subtracting 360 from negative 315. Then we get negative 675 degrees. All right, so those are just some answers that you could have gotten. You may not have the same number of answers, but those are some possibilities. You may not have the same exact numbers. Okay, try number 49, and when you come back, we'll do it together. All right, we're back, so let's add 360 to 1 degrees, and we get 361. That's a coterminal angle. Let's subtract 360, and then we get negative 359 degrees. That's a coterminal angle. And let's try adding 370 2 times. So we rotate twice, starting from 1 degrees, and we get 721 degrees. So those are just some possible answers that you may have gotten. Okay, so those are coterminal angles. You just keep rotating 360 degrees, 360, 360, or in the opposite direction, negative 360, negative 360, negative 360. Now, the biggest or the most important question that we need to address is, why do we care about coterminal angles? Well, I mean, what's the point? Why do we care? The reason that we care is the trigonometric value, the value of trigonometric functions of coterminal angles. They're all equal. So let's say you choose sine. If you plug in coterminal angles, these yellow angles just happen to be all coterminal, into that function, you're going to get the same answer. Because the reference triangles that are going to be created are all going to be the same. So if this 35-degree angle is in quadrant 1, well, this angle is in quadrant 1 too, and it has the same reference angle. This angle is in quadrant 1, and it has the same reference angle. So because the coterminal angles have the same reference triangle, the same reference angle, they must have the same value, the value of each trigonometric function. Now, cosine is not going to be equal to sine. It has to be the same function in order for this to work. So these problems tell us to use a calculator to show that the following statements are true, then draw a reference triangle in standard position to show why each statement is true. So let's calculate the value of sine 35. So if you're using a graphing calculator, you want to push the sine button first, then enter 35 degrees, and then press the enter button at the bottom right. If you're using an iPhone, you enter 35 first, then push the sine button, and make sure that your phone is rotated so that it's in landscape mode. And what you get is 0.5736 approximately. We're just going to round off. And if you calculate the value of sine 395 degrees, then you get the same thing, 0.5736. And same thing with this value here. So you can enter those into your calculator and verify that you get the same number. That's why we care about coterminal angles. They all produce the same value. And that should be an approximately equal to symbol. These numbers are exactly equal to each other, but the reason we have approximately symbols is because the numbers are not actually 0.5736. We're rounding. And so now let's draw these angles. This is a 35-degree angle, roughly. And so we have our reference triangle. It's in the first quadrant. But if we draw a 395-degree angle, we rotate 360 degrees and then go 35 more, and guess what we have? The same exact triangle. And the reference angle is 35 degrees. It's kind of hard to draw it in that little space there, but you get the point. If we rotate negative 325, then we rotate negative 90, 180, 270, and then a little bit more until we get to the same exact triangle. These triangles don't look exactly the same, but they're supposed to be exactly the same pretty much. So that was negative 325. And the reference angle, again, is 35. If the reference angle is the same, and we're in the same quadrant, in this case quadrant 1, then you can see that we're going to get the same value. That's what is so important about coterminal angles. So let's do this problem down here. We get the same thing. Let's rotate 235. That'll get us to about there. roughly. So our reference triangle is now in the second quadrant, and the reference angle, 235 minus 180 is 55, so the reference angle is 55 degrees. If we rotate 125 degrees, we have the same triangle in the second quadrant. These triangles should look exactly the same. I'm not drawing them exactly the same, but you get the point. So this is how, or this is why these reference angles are so important. 485 will get you to about there. And again, we have the same reference angle. If you were to calculate the reference angle, it would be 55 degrees. So on our calculators, let's compute the tangent of a negative 235 degree angle, and we get negative 1.4281. And if we calculate the tangent of a 125 degree angle, we get again negative 1.4281, and so on and so forth. So this is just demonstrating why coterminal angles are so important. So now it's time for you to try. Go and attempt this next problem. You want to calculate these values with your little handheld computer, your graphing calculator, or your iPhone, or your scientific calculator. Go ahead and calculate cosine 310 with your calculator, and verify that it's the same for all these values. They produce all the same value. Okay, so you should have gotten 0.6428 roughly if you round off, and you get the same value for every expression that we wrote there, because they're all coterminal angles. And if you were to show why this is true, go ahead and draw these angles in standard position and the corresponding reference triangles, and see if you can show why the values are all the same. Okay, we're back, so let's rotate 310 degrees, which would take us to about there. And it looks like the reference angle is going to be 50 degrees. The reference angle is always the angle between the x-axis and the terminal side of the angle in question. If we rotate negative 50 degrees, then we'll start here and go to about there. Again, we get the same triangle. Same triangle, same position, same reference angle. But now it's negative 50. And let's rotate negative 410, so we're going to go clockwise because it's a negative angle. We'll go 310 or 360 degrees, and then 50 more degrees, and again you see we get the same triangle. That's why coterminal angles are so important. So it's the same 50 degree reference angle, and the triangles are all in the fourth quadrant. Alright, so I want you to do the same thing for the next problem. I want you to use your calculator and verify that the sine of every coterminal angle is the same, produces the same value, and I want you to draw the triangles to show why we get the same value. When you come back, we'll do it together. Okay, we're back. So if we use our calculators to find the sine of 200 degrees, we get negative 0.342 approximately. So if you got that number, good job. So at this point, go ahead and draw the triangles to demonstrate why we get the same number for each one of these functions. And when you come back, we'll do it together. Okay, we're back, so let's rotate 200 degrees. That would take us to about here. And the reference angle is about 20 degrees. It's kind of hard to draw the reference angle there. It's kind of a cramped position there, but we'll just say 20 degrees. Now let's rotate 560 degrees, so that's one complete rotation, 360, plus another 200 degrees, and guess what? We end up at the same place. They're coterminal angles, so we get the same reference triangle, and most importantly, the same reference angle, 20 degrees. Let's try rotating negative 160 degrees, and we get to about there, and of course, we have the same triangle with the same reference angle. So all the triangles are in the third quadrant. They all have the same reference angle, and therefore, if you were to calculate these values, you would get the same number. So the big question, obviously, is who cares? If you got those graphs, good job. Why do we care about the idea that coterminal angles produce the same output with these functions if you're plugging them into the same function? Why do we care about that? Well, it's going to become very useful throughout this course. If you're given a simple trigonometric equation, this is called a trigonometric equation, you're going to be asked to find theta. What is the angle that you would need to plug into that function in order to produce this output? So what we're doing at this point is we're going in the opposite direction. In previous classes, we plugged in a number here, and I asked you to find this green ratio. Well, now we're going backwards. Now I'm giving you this green ratio, and I'm asking you to find the angle. So how do we do that? That seems really difficult. But you may recognize this ratio. That's the most important thing, is to recognize that ratio. Sine theta, we're told, is equal to negative root 3 over 2. But what if we change that to negative x root 3 over 2x? That looks very familiar. There's only one type of right triangle that fits this description, and that's a 30, 60, 90 degree triangle. So what is the angle? If you have this ratio, what is the angle theta? Well, the side opposite the reference angle, the 60 degree reference angle, is x root 3. And so obviously the angle is 60 degrees. But there's a problem. It's negative root 3 over 2. When we try to solve these equations, we can consider 4 situations. When the triangle's in the first quadrant, the second quadrant, the third quadrant, or the fourth quadrant. If you have a triangle with a reference angle of 60 degrees in the first quadrant, then sine theta is equal to positive root 3 over 2. If you have an angle where the triangle is in the second quadrant, and that angle would be 120 degrees, you would have to have a 120 degree angle to produce a reference angle of 60 degrees in the second quadrant, then sine again is equal to root 3 over 2. But if your triangle is in the third quadrant, as we see down here, then you would have a sine value that is negative root 3 over 2. Again, these are all 30, 60, 90 degree triangles, and the reference angle is 60 degrees. If your triangle's in the fourth quadrant, then again, you get negative root 3 over 2. So the third quadrant and fourth quadrant triangles work. So what are the angles that you have to plug into the function? Well, if this green angle is 60 degrees, then the red angle would have to be 180 plus 60, which is 240. Again, you rotate 180, and then you go 60 more, and that's the red angle that we're looking for. So one of the answers is 240 degrees. Theta is equal to 240 degrees, but this angle over here works also. What is that angle? You rotate all the way around, and then there's 60 degrees left for a complete rotation. Well, that's obviously 300 degrees. Again, that's just basic arithmetic. Now, we can actually keep going. We can actually keep rotating around and around and around. I can find all kinds of coterminal angles for these angles down here. I don't want coterminal angles for angles up here, because those are not going to produce negative root 3 over 2. They produced positive root 3 over 2, as you can see up here. That's not the right value we're looking for. We want to know what values produce negative root 3 over 2. So I can just keep finding coterminal angles that land in the third and fourth quadrant with reference angles of 60 degrees, and there's actually an infinite number of answers. There's an infinite number of solutions. I can have positive numbers, or if I rotate clockwise, I can have negative answers. So we don't want to write an infinite number of solutions, so that's why the problem says find theta between 0 and 360 or equal to 360. So we only have to find the values that are between 0 and 360, and these two numbers that we found are the only values between 0 and 360 that work. So there you go. Here's another example. If secant theta is equal to root 2, find theta. But again, theta is only going to be between 0 and 360. So what we do is we try to recognize that ratio. So we can write root 2 as root 2 over 1, and then change it to x root 2 over x. And now we see something familiar. It looks like a special triangle. The hypotenuse is x root 2, and the adjacent side is x. So you can see that this is a 45, 45, 90 triangle. So there are 4 triangles that we're going to consider, one in the first quadrant, one in the second quadrant, one in the third, and one in the fourth. And we're going to ask ourselves which of these secant values produces a negative, or excuse me, we want a positive root 2. So that happens in the first quadrant and the fourth quadrant. So one of the answers is actually 45 degrees. The first quadrant up here, one of the answers is 45 degrees. If you plug in 45 degrees, you're going to get positive root 2. So theta is equal to 45 degrees. But another answer is down here. That's going to be, how many degrees would that be? That's 315 degrees. Again, a complete rotation is 360. Subtract the green, and you get 315. So those are the two answers. Those are the two theta values that will produce positive root 2. If you plug in these other values, 135 or 225, you'll get positive, or you'll get negative root 2. We don't want negative root 2, we want positive root 2. So these problems are pretty challenging because we're going backwards. So let's try one more before you attempt one on your own. So tangent is equal to negative 1 over root 3. And we're looking for the theta values that would give you that ratio. So we can change that to negative x over x root 3. And now we can kind of recognize the relation between the sides. Again, tangent functions only apply to right triangles. And if we say that the opposite side is x and the adjacent side is x root 3, and we assume that one of the sides has to be negative and one's positive, we can see that this is a 30, 60, 90 degree triangle. So now we place a 30, 60, 90 degree triangle in every quadrant, and 30 is the reference angle because, again, the opposite side is x, so 30 is the reference angle. So placing these triangles in each quadrant with the reference angle equal to 30 degrees, we have all these possibilities. And the question is, which one of these scenarios produces a, what do we want? A negative 1 over root 3. Which one produces a negative 1 over root 3? And the answer is the second quadrant and the fourth quadrant. So if you just do the basic math, you see that the second quadrant and the fourth quadrant produce negative 1 over root 3. So just doing basic arithmetic, this is going to be 150 degrees. That's one solution. And over here, it's going to be 330 degrees. That's another solution. So the answers, and again, we're only finding the answers between 0 and 360. The answers are 150 degrees and 330 degrees. Those are the theta values that you can plug in to the tangent function to get negative 1 over root 3. Now again, we're only looking for the solutions between 0 and 360. There's actually an infinite number of solutions, an infinite number of coterminal angles that will produce the same value if you plug them in to the tangent function. But we're only looking for solutions between 0 and 360. So I want you to take pictures of these problems that we just did. And I want you to use those problems to help you do number 57. So go ahead and try 57. When you come back, we'll do it together. Okay, we're back. So we're told that cosine theta is equal to 1 over root 2. But if we write it as x over x root 2, we can recognize it as a 45, 45, 90 degree triangle. So we place a 45, 45, 90 degree triangle in the first, second, and third, and fourth quadrants. And we simply ask the question, which one of these scenarios will produce positive 1 over root 2? And the answer is 2 of those scenarios will produce positive 1 over root 2. This scenario in the first quadrant, and this scenario in the fourth quadrant. So those are the answers. So in the first quadrant, the angle is actually equal to the reference angle. So that's one of our solutions. Theta can be 45 degrees. But over here, what is that angle? That angle is going to be 315 degrees. Again, just using basic arithmetic. So those are our solutions. Again, a complete rotation is 360. Subtract the green angle and you get 315. If you plug in those angles into the function, you're going to get positive 1 over root 2. So if you got that one right, good job. Try number 58. And when you come back, we'll do it together. Okay, we're back. So we're told that cosecant theta is equal to negative 2, which is the same thing as negative 2 over 1. And if we write that as negative 2x over x, we can see, and by the way, we know that that negative has to be down here because the hypotenuse is never negative. We can see that this is going to be a special triangle. There's only one right triangle, one type of right triangle where this occurs, and that is a 30, 60, 90 degree triangle. So we put the 360 or 30, 60, 90 degree triangles in the first, second, third, and fourth quadrant, and we ask ourselves which one of these scenarios will produce -2 for cosecant theta. And of course, we have these two scenarios here. So we have to ask, what are those angles? Well, this angle is 180 plus 30, which is 210. And this angle is 360 minus 30, which is 330 degrees. So the two solutions to the equation, if cosecant theta is equal to -2, then theta must be equal to 210 degrees or 330 degrees. So if you got those right, excellent, perfect. This is really not easy. The concepts that we're doing right now are pretty convoluted. But this is the foundation of the entire trigonometry curriculum. And once you get used to these types of problems and how this works, the rest of the course is going to be easy. So go ahead and try number 59. When you come back, we'll do it together. All right, we're back. So we're told that cotangent theta is equal to 1, which can be written as 1 over 1. And we can also write that as x over x. So the adjacent side and the opposite side must be the same length. But if that's true in a right triangle, you must be dealing with a 45, 45, 90 triangle. So what we do is we place 45, 45, 90 degree triangles in every quadrant, and we ask, in which quadrants do we get +1 for cotangent? Because the problems tells us we want cotangent theta to be +1. And the answer is the first quadrant and the third quadrant. Because the adjacent side and the opposite side in the third quadrant are both negative. You divide them, you get a positive. So, one answer is the first quadrant answer, which is the reference angle, 45 degrees. And the third quadrant, we have 225 degrees. Because you rotate 180 and 45 more, so that's 45 plus 180 is 225. So there you go. If you got that one right, excellent. So we're just going backwards. Instead of giving you the angle and asking you to find the ratio, we're giving you the ratio and asking you to find the angle. The problem is there's an infinite number of angles that will give you a ratio of 1. There's all kinds of coterminal angles. You can just go around and around and around and around. But and you can also go in the negative direction, the clockwise direction. But we're only asked to find the solutions between 0 and 360. So as you can see, this stuff is pretty involved. It's pretty convoluted, pretty difficult stuff. But once you get used to it, you see that it's a different language that you have to learn. But once you know that language, it's going to be very easy to calculate these values. So that was the class today. Let's take screenshots of all the work that we did to help you with your homework or to study for tests. Here's screenshot number 1. And number 2. Number 3. And 4. Number 5. 6. 7. 8. And 9, but don't go before you get your homework. Remember, the homework is the most important part of this course or any math course. So here's screenshot number 1 of the homework. and number 2. And number 3. Number 4. Number 5. Six. And 7. And here's the answers. Here's screenshot number 1 of the answers. And screenshot number 2. So get that homework done completely, correctly, and neatly. And I'll look forward to seeing you in the next class.